I've been excited for this conversation, Katie, because I've mentioned it online a few times, but I don't know if I've talked to you about it. I've been having the depression.
Mm-hmm.
And it's not been fun. It's been challenging. But in this process of kind of going through a period of darkness and difficulty, I have taken an astonishing amount of solace in this project that we've been doing.
Oh, good.
I've been thinking about my protons and how complicated they are, and how, of course, it's difficult for a collection of protons this large to make it through together, sticking together, as a body must. And it's made me think a lot about what you're calling the astrophysics of life.
Mm-hmm. Right.
But I realize I don't actually know anything about the astrophysics of life. And so it's had me thinking speculatively, but I'm excited for this conversation because after it, hopefully I'll be able to think in a more grounded way about the fact that I'm Big Bang stuff and understand a little bit more about the relationship between the universe and me. A reality I've faced over and over again as I've had these conversations with Dr. Mack is how insignificant life on Earth is in respect to our universe. Not only are we living on a speck of dust in a tremendously vast space, but even the type of matter we're made of is an afterthought compared to dark energy and dark matter. That negligibility, our sheer smallness, can evoke a sense of wonder, but also a sense of futility. So life typically does not factor into cosmology. But what about the inverse? How does cosmology factor into life? Well, here's our conversation.
I should say, before we start, that my usual area of research does not touch life in any way. But there are some very clear things that we can say as astrophysicists about the relationship between the cosmos and humans and like what we are made of and how life works. So I think that one of the things that we've talked about before, but I think is good to reiterate, is what you just mentioned, that we are Big Bang stuff. If you think about like what we are made of by mass, if you just kind of add up all of our molecules and atoms and stuff, by mass, we're mostly oxygen and then carbon and then hydrogen, nitrogen, phosphorus, calcium. But if you count by the number of particles that we have in us, like the number of atoms, by number, we are vastly more hydrogen. So we're something like 63% hydrogen.
Wow.
The hydrogen nuclei, the protons, those do come just right from the Big Bang and may or may not have ever been inside a star. That's just the Big Bang made a bunch of protons, and those protons became us. Most of what we are made of is that stuff that came from the Big Bang and has not become another kind of atom.
So it's not even like a processed hydrogen. It's a raw, unfiltered, organic hydrogen straight from the source.
Yes, exactly. Yeah, so some of the hydrogen has been through stars, but a lot of it is just, it was in space. It was part of the cloud of gas that the Milky Way formed out of and the cloud of gas that the solar system formed out of and became us, right?
Wow.
Became the stuff that we are made of, those protons, those hydrogen nuclei. Now, the rest of the atoms in our body, the oxygen, the carbon, the nitrogen, the calcium, the phosphorus, sulfur, all of that kind of stuff, that was formed inside stars. So in order to make us, we needed to get together not just the protons, but a bunch of these heavier elements that can make structures, can make, solid materials, that kind of stuff. So the Big Bang made hydrogen, helium, a little tiny bit of lithium, maybe a little tiny bit of beryllium, but was mostly hydrogen, and everything else gets formed in stars or through some other process involving stars, involving cosmic rays, that kind of thing. So if you look at like the other stuff we're made of, so carbon was mostly made in low mass stars at the end of their lives. So like stars like the sun, when they die, they create this, sort of big nebula, blow off their outer layers, and there's processes that happen inside and that makes some carbon. And then also massive stars, when they explode, that creates some heavier elements. Carbon is one of the things that's made in that. Nitrogen is kind of similar. Oxygen is mainly made in the explosions of massive stars. And then, calcium, phosphorus, sulfur, those are all kind of similarly mostly in these massive star explosions, sometimes in exploding white dwarfs. So stars are creating everything else that we're made of. There are some elements that are mostly made when cosmic rays slam into other particles and break them apart. And so you get like beryllium and boron and a little bit of lithium. Some of those are made from like cosmic rays, like cracking open other atoms, like doing fission. But for the most part, you look at most of the periodic table and it's massive stars or end-of-life processes of stars. And the reason for that is that you need a lot of energy to create heavy elements. And I think we've talked about this to some degree where, with like a star like our sun fuses hydrogen into helium in its core. That's pretty much all the sun is going to do. At some point, it's going to run out of hydrogen in the core. It's going to puff out. It's going to make a few heavier elements in this sort of end-of-life process, but mostly it's just going to do hydrogen to helium. But more massive stars have processes going on in their cores that can fuse heavier elements. They've got way more temperature, higher temperatures, more pressure, and they can squish together all these elements. When it gets to iron, you can't fuse iron and still get energy out, and so then things get more complicated, and the things heavier than iron, you really need like supernova or some kind of much more complicated process to get those heavier elements. You can make some amount of heavier elements inside the core of the star, and then most of the stuff that's made is really in the supernova explosions.
And we can literally just look at the periodic table, and that will tell us how massive an element is and like where it fits in that realm, right? Not really?
Well, sort of, yeah. I mean, you can look at the periodic table and see the masses of the elements.
Yeah.
There's a little bit of some subtleties to how those fusion events happen. And
I don't doubt that, man. I mean, the subtleties involved in just like what a proton weighs has thrown me for an absolute loop. So, but in general, if something's heavier than iron or not heavier than iron.
Yeah, but the thing is, like, so when I first started learning about stellar fusion, like about stars making heavier elements, I thought like, you kind of first learn about like massive stars burning carbon and nitrogen and oxygen, and they make sort of shells of heavier elements in the core, and I kind of thought, okay, so that's how it happens. You create these shells of these different elements, and then those are the element that gets kind of blown out into the universe, and that's how the right. So like when the star explodes, that gets spread out, and that's how we get all the iron and oxygen that we need. Yeah, but like a lot of it's actually formed like during the supernova. So like a lot of the carbon that's formed in the core of stars kind of stays there in the remnant, depending on what kind of star it is. But, the supernova itself is not just something that spreads the elements, but it's also part of what makes the elements. So you dump so much energy into all this material so quickly, a lot of that creates a lot of these heavier elements. So it's a mix between some of the stuff is just formed in the star and gets dispersed, but in a lot of cases it's really those explosions that have to happen to create most of like the periodic table.
Okay.
And to create a lot of that, a lot of the stuff that's coming out. So there's some interesting subtleties that I was kind of reading about last night, and I got a little bit fixated on carbon. And I wasn't sure how much we wanted to talk about carbon specifically.
I love talking about carbon because, one of my obsessions is biomass, global biomass, like what is life on Earth actually made out of? And the way they determine that is by number of carbon atoms.
Right, yeah. Yeah, so carbon is a super useful atom for life, for creating any kind of complicated molecules. There's a lot of it. It's very abundant in the universe. And it has the ability to form these 4 bonds, right? So it has 4 valence electrons, which means that there's kind of 4 places you can kind of attach to a carbon atom. And that means that you can create really complex chains, really complex structures with that carbon, very stable bonds. And you can also form really strong double or even triple bonds with carbon because of the way that the electrons are set up. And so it makes a really great basis for something as complicated as life. And all life is kind of based on carbon as far as we are aware. In science fiction, people talk about like silicon-based life because you can have sort of similar things going on. But in practice, everything we've seen is carbon-based. So the carbon is forming kind of the backbone of the stuff that life is made of. There was this weird bit of history around people trying to understand how nuclear fusion in stars works, where they ran into this problem with carbon, which is that like it's reasonably straightforward to create, helium out of hydrogen. There's a kind of chain of processes that happens, but the energetics kind of works out in a way that makes some sense. Creating carbon in a star is kind of complicated in a way that, like, for a long time, scientists kind of couldn't figure out how that could even happen. So what you need to do that is you first fuse together 2 helium nuclei, helium-4. So that's helium with 2 neutrons and 2 protons in the nucleus. You fuse the helium-4 together to make beryllium-8. And then somehow you need to get another helium to combine with the beryllium to make carbon-12. Okay, so beryllium has 4 protons, then, add 2 more, you can get, you got to do something complicated. You can get carbon-12 out of that in principle. But in practice, that beryllium is really unstable and just decays very quickly. And if you throw the helium into the beryllium, that's also really unstable and decays really quickly. And so you end up with this situation where it just doesn't seem like there should be enough time to create a lot of stable carbon.
Right. So we're living in a universe that has more stable carbon than we would anticipate based on carbon getting made that way.
Yeah. And there was a lot of discussion of, like, can you even get all of those elements to fuse? Do you need like ridiculously high temperatures? So the first calculations needed like billions of degrees of temperature to get this fusion to even happen in the first place. There were some revised calculations. They had to figure out quantum tunneling, because before they knew about quantum tunneling, they couldn't even figure out how to get any of these fusion events to happen, because these nuclei would be positively charged. They would repel each other, and they wouldn't get close enough for the strong nuclear force to take over for them to actually fuse. So they had to figure out quantum tunneling, get them to actually fuse, but they knew these decay times were really, really fast. And so there was this effort to like figure out how carbon ever happens. And Fred Hoyle, who's a famous astronomer, and he was an interesting figure because he also was like super opposed to the idea of the Big Bang. And he thought that there must be a steady state universe. And I think this was sometime around like the 20s or 30s, or I don't know exactly the dates, but it was early on there. He was trying to figure out how carbon could be made. And he figured out there had to be some kind of like resonant state, so some kind of excited state of a carbon nucleus that would allow it to more favorably like form from the beryllium and the helium. And then that state could decay into the ground state of carbon-12 that is kind of stable, right? And so he just predicted this state had to exist. And he wrote down what the energy of it had to be. And he's like, this has to be there, or else, carbon can't happen in any reasonable amount. And then subsequently, he convinced some experimentalists to do some experiments and try and find this excited state of carbon. And they found it, and it was there. It was where it had to be, because if it hadn't been there, we wouldn't have carbon. And Hoyle was like, we have to have carbon. There has to be this state. And so he predicted it. Turns out there's this excited state. 1 in something like 2,000 times, that excited state will decay to carbon instead of everything just decaying into helium nuclei again. And that's enough to allow carbon to be formed at reasonable levels in stars.
There's just so many things that had to go right.
Yeah, it gets weirder too.
Like, you talked about fine-tuning in the past, but like this feels like And I know that, like, we're biased because we live in the universe that ended up happening, right? And so, like, that's going to bias us. But it is so weird that we needed that to happen 1 out of every 2,000 times so there could be carbon, so there could be us.
And it's one of these things, like, when you look this stuff up, because I was reading about this to prepare to talk about it, because I've only kind of read about it a little bit in the past. And a lot of the sources you find for it are like, well, this proves God.
Yeah. I definitely recall people telling me over the years that the universe's bias toward carbon is the best indication of a god.
Yeah, I mean, and I don't think that's a particularly compelling argument, but it is a fascinating process. And it gets even more interesting because once you have carbon-12, you need to make oxygen, and you do that by throwing another helium nucleus at carbon-12. And if there were a resonance in that state also, then all the carbon-12 would just turn into oxygen, and then you wouldn't have carbon again. And so Hoyle predicted, okay, so now there can't be an oxygen resonance state, and there isn't.
Wow.
Turns out. And I was reading up on this, and some people had calculated that if you had like a 0.5% change in the strength of the nucleon interactions, then stars would either all make carbon or all make oxygen, but not the other one.
Wow. And so either way, if it went this way or that way, there's no us.
Yeah. And so it's this kind of wild, I don't know if it's a coincidence or just something that because we see it has to have existed.
Right.
But there's this kind of interesting set of circumstances where it's just not as straightforward as you might think to form all of the elements that we need to form in order for like us to exist.
And I know that you don't like it when I apply scientific reasoning to real life, but isn't that also true for humans, right? Like for individual human lives? Like it's very easy for me to say like, oh, if Sarah hadn't taken that boxing class, we would have never met and we would have never had kids and so our kids wouldn't exist. Well, that's true. Right. But like if Sarah hadn't taken that boxing class, something else might have happened.
Right. So in science, we call it the anthropic principle, like this idea that like it's tricky to assign probabilities to things and so on when not having that observation would mean you cannot do that observation. You know what I mean? Like, so often the anthropic principle is applied to like, we live on the surface of a planet. We don't live in the middle of the sun. And that's not because there's more space on the surface of the planet than in the middle of the sun. It's just because if we lived in the middle of the sun, we wouldn't be living and we wouldn't be able to say that we live in the middle of the sun. We just wouldn't exist, right? So the fact that we live on the surface of a planet means we can talk about living on the surface of a planet. And so that's a kind of anthropic argument for the fact that we live here, or we live in the habitable zone of our solar system, right? We live in a part of our solar system where liquid water is possible. If we lived on, the surface of Neptune or something, liquid water, it's impossible. We wouldn't be living. We wouldn't be there to talk about it. Stuff like that.
And yet it is also true that it's astonishing that Sarah took that boxing class. Like what, and it's astonishing that we ended up existing. Like the fact that anything exists at all. My main conclusion from 7.5 episodes of learning from you is the fact that anything exists at all is a real mind blower.
Yes. Yeah. No, I'd agree with that. And I guess the thing that I'm constantly finding out is just all of the kind of the nice little stories we have about, this happened, then this happened, then this happened. It's all just so much more complicated than that if you really dig into it. And the things that feel like inevitabilities are kind of not. Like life is kind of not an inevitability of chemistry in some sense, right? Or nuclear physics. I mean, in the sense that like nuclear physics might have happened differently in a way that was not going to ever set up the conditions for chemistry in life. Right. And, it's nice that it came out this way because existence is cool, but it's also not something that is like, it was written into the laws of physics that we were going to be here and talking about, the universe.
So you don't think that there's necessarily anything inherent to the laws of physics that made life or us inevitable?
Given the constants of nature that we observe, you can draw a straight line in some sense from the Big Bang to us, right? Because you do get to this point where it's like, okay, Big Bang makes hydrogen and helium, and then hydrogen makes stars, and stars make more helium and make all these other elements. And because the nuclear interactions are what they are, it's possible to create these heavier elements, and those are going to collect into rocky planets. And then those rocky planets are sometimes going to have life because of a sort of process of chemistry to biology that happens. So in that sense, yeah, I mean, I don't know if it's inevitable, but there's a clear through line. There's a clear story that goes there. But at some point, I guess one wonders if the constants of nature as they are were inevitable, right? And that comes into questions about like kind of about multiverse ideas, about this idea that maybe there are regions of the universe where the laws of physics are different, which could be the case. You know, when people talk about multiverses, usually in fiction, what they mean is like the many worlds interpretation of quantum mechanics, this idea that every time a quantum event happens, the universe splits into two, where it went different ways. That's what people use for like fictional parallel universe stories, stuff like that.
Great for fiction.
Great for fiction. But in physics, a lot of what we mean when we talk about multiverses is just the idea that there could be different regions of a larger space that includes our observable universe, but beyond that as well, in which laws of physics might be different. You know, the circumstances, the environment might be different, and different things could happen. So there could be regions of this larger multiverse where the nuclear interactions are slightly different and chemistry can't happen. Or maybe it happens very, very differently. I don't know.
So that could be another anthropic bias that we happen to be in this situation.
Yeah, and that's how anthropic principle comes up most often in physics, is this idea of, you know, I mean, essentially, we don't know why the constants of nature are what they are in a lot of cases. Like, the biggest one that people complain about is the value of the cosmological constant. So the strength of dark energy, essentially. We don't know why dark energy is here, but not zero, right? Or not large. Like the cosmological constant is kind of small in some sense that makes sense if you're talking about the value of this number. And so, you know, we get this acceleration, but not until the universe has existed for many billions of years. And, you know, it doesn't prevent the existence of galaxies and things. It just, after they've existed for a long time, then at some point they're going to not form anymore. You know, so there's this weird middle place where the cosmological constant is small, but not zero. And people use anthropics to argue that that makes sense, because a lot of predictions from first principles, depending on what your sort of starting assumptions are, might lead you to a cosmological constant that's either zero or very large. And a universe with a very large cosmological constant is not going to have planets. It's not going to have galaxies. Like it's going to be accelerating too fast, too quickly for structure to form. A cosmological constant of zero is not a problem, really, for the formation of structures. So arguing that it should be small but not zero is a little bit tricky, but people use anthropic arguments to argue that it should be small or zero, and the fact that it's small is maybe just because of, you know, chance in this bigger space. But it's tricky to make those arguments because you can't really place probabilities on where we end up in this larger space with different values in a way that is consistent. You have to put in a whole lot of assumptions, and the anthropic principle can kind of help with that, but it can't push you to exact numbers in certain ways, and so then you have to do something more complicated. So that's how it usually comes up, is something to do with dark energy or maybe even dark matter. But yeah, it could apply to this, you know, carbon thing as well, right? Like,
right.
We wouldn't be here if the carbon resonance weren't there, right? So
yeah, but it is. And we are.
Yeah, so it's an interesting question. Yeah.
So every element we are made of either comes from the Big Bang itself or was made by stars, from their core or as a result of them exploding. That adds a bit more of a wow factor to the periodic table for me. And it turns out it's very difficult for stars to create a stable version of carbon, that element essential to life as we know it. Physicists had to discover quantum tunneling, the ability of some particles to tunnel through barriers, and an excited state of carbon to prove it was even possible. And for us to exist, they also had to determine that oxygen didn't have an excited state. Add that to the fact that we live in a part of the universe that allows liquid water to exist, and that we have just enough dark energy to allow planets to form, and life can seem inevitable. But the existence of the building blocks of life was not inevitable. And knowing what we know, it might even have been improbable. So I want to ask if I can take you forward to the rocky planets. These rocky planets are forming. I don't really understand how, but I trust you that they formed.
We can just kind of walk through how we got here.
Great.
From the beginning of the solar system. So the solar system has been around for something like 4.5 billion years, maybe just a little bit longer than that. So the sun formed somewhere around maybe 4.6 billion years ago. So the universe is 13.8 billion years old. It took a while for the sun to form. And, it's not surprising really that we weren't formed way, way earlier, because you need a certain number of generations of stars to create enough heavy elements to create rocky planets and life. And depending on what kind of environment you're in the universe, that can take a while. I mean, if you were in an environment where there are lots of stars forming very, very quickly, like in a really rich center of a galaxy cluster or something like that, then those timescales can be very short because massive stars don't live very long. You can, in some handful of millions of years, you can have a situation where stars are forming and you're creating a lot of heavy elements. In the part of the universe that we're in, it took about 3 generations of stars before, like our star is about a 3rd generation star as far as we know. So a couple of generations of stars did their supernovae, created their elements, polluted the interstellar medium. So we call it pollution. That's
a great line. Polluting the interstellar medium.
Yeah. Or enrichment. Sometimes we say enrichment when we're being nice about it.
Enriching feels better than polluting.
Yeah.
I'm quite fond of the idea that we're sort of living in some kind of galactic suburb, and so things just happen a little later here. Like the way that a little further out from the city, people might find out about the hot new band a few months after the folks downtown.
Yeah. And there's arguments about a galactic habitable zone. This idea that if you live too far out or too far in a galaxy, things are not as suitable for life. So too far out, you just don't have enough heavy elements. Like there aren't enough generations of stars. You don't have enough enrichment. Too far in, you have to deal with there's a supermassive black hole. There's a lot of radiation. There's, maybe stars forming very, very quickly, going supernova a lot. And it's just dangerous. It's just a dangerous place to be because you're going to get zapped by something before life can really develop. And that's a very poorly defined kind of region of the galaxy, but we're inside a region where it seems like that's a reasonable place to live. It's a decent kind of neighborhood for, it's not too boring, it's not too scary.
Right. So we live in a decent, not too boring, not too scary region of our galaxy. And as a result, this 3rd generation star was able to form about 4.6 billion years ago.
Yeah. And so what happened was you had a big cloud of gas and dust and it coalesced and created a disk of material, and the sun formed in the center where it was really dense. There was a lot of material there. And then the disk, at first it was like a protostellar cloud, and then it was the star, and then there's this protoplanetary disk, and it's just a disk of gas and dust and little bits of metals or whatever material from that protostellar cloud, and that slowly coalesces into planets. So planets sort of form in these eddies in this these little knots in this disk, and for a long time there's collisions between these protoplanets and, everything's really chaotic. But eventually the gas and dust in this disk gets kind of, hoovered up by the forming planets. And you end up with a stable set of planets going around.
Okay.
And we still don't have a very good understanding of that whole process. It's a complicated process. You get lots of different kinds of solar systems that form, some with really massive planets really close in, called hot Jupiters. Those seem to be pretty common in the universe. We're not entirely sure how that goes. We don't entirely know why the planets are distributed the way they are in our solar system. And there are some tricky bits, going from certain scales where it seems complicated to get the material to stick together at those scales and not bounce off. And so planet formation is a complicated science. But eventually you end up with, we have this sort of hot protoplanet, sort of molten because everything's kind of been crashing together. That's the young Earth. And then it gets crashed into by something about the size of Mars. And that creates a, blob of material that sort of shoots out and becomes probably some kind of ring and then turns into the moon. That's the story that we think is happening there. And so then we have the Earth and the moon, and over time, the Earth cools, and at some point in this process, it sort of develops water. Maybe the water was kind of already there. Maybe comets came in and brought in water. It's a little bit unclear. It seems like probably the water was already there, and then it kind of was able to collect on the surface. And the moon is kind of possibly helpful for life, and we're not really sure of the details of that, but it sort of stabilizes the seasons a bit. So having a large moon might be helpful for life, but at this stage, it doesn't really matter because at this stage, it's just, there's water, there's rock, the Earth is still kind of warm. And we think that probably life began near a hydrothermal vent under the ocean, most likely.
That seems like a good place, right? That seems like a good place for chemistry to happen. It's warm, it's wet.
Yeah. What you really need for life, as far as we understand it, is some kind of source of nutrients. So you need chemicals that can react with each other. You need energy. And specifically, you need a gradient of energy. There needs to be a way to move energy from one place to another, right? So you can't just be in a uniformly hot space or something. It has to be possible to, move the energy. So, maybe sunlight is a source of energy coming from outside and you can do something with that, or something like a hydrothermal vent where you have the hot hydrothermal vent in the cooler ocean and you can extract energy from that. And then you need a liquid and probably water. It seems like, all life on Earth involves water in some way. That's the liquid that life on Earth uses. There's speculation that maybe you can use other liquids as the thing that allows the chemicals to move around. People talk about the possibility of life in the methane ocean on Titan. Possibly. It's unclear. It's unclear if you can use other liquids, but water seems to be the one it's the one everything on Earth uses. And it's how we define a habitable zone. When we talk about a habitable zone of a solar system, is there's kind of a distance from the center of the solar system where you're close enough to the star that it's possible for water to exist as liquid, but not so far that it's all ice, right? So you don't want it to be either steam or ice. You want it to be able to be liquid on the surface of the planet. And that's all ill-defined because you could also have, a really thick atmosphere that would make it so that everything is too hot for liquid water, like on Venus. So Venus is nominally in the habitable zone of our solar system, but it's too hot for life. Life as we know it anyway is too hot for liquid water. And then Mars is nominally also in the habitable zone, but it's got basically no atmosphere. And so
it doesn't have enough atmosphere to have liquid water.
Yeah, it's a little bit too cold. There are times of the year and places on Mars when it can be above freezing on the surface, above 0 Celsius, but because the atmosphere is so thin, you can't have liquid water. Mm-hmm. The ice will sublimate, but that's it.
So you don't just need to be in the habitable zone. You also need to have the right amount of atmosphere so that you can have liquid water.
Yeah.
And that probably took time to develop on Earth, I would imagine.
Yeah, so at some point we had liquid water. So we had this hydrothermal vent. And probably what happened at that place is that you had a bunch of chemicals and you got this chemistry kind of happening. And then that chemistry sort of by chance created some stuff that's like the ingredients of RNA. So we think it's probably started with RNA. And then there was this sort of what they call molecular natural selection, which is just kind of like lots of sort of interactions between molecules that are kind of random, but then some are like a little bit more likely to happen. And then that turns into biology and actual natural selection. You get these first RNA cells, and then those evolve into DNA. And that whole process is very complicated, but there's a kind of logical progression that scientists have worked out where you can go from very simple sets of organic molecules like amino acids and things, and through a lot of time, we're talking probably 1 billion years or something, maybe 500 million years, I don't know, somewhere around there, to go from these simple chemicals to life. But if you have a whole lot of these chemicals, a lot of water, and a lot of time, just from the bouncing around, from the energy injection, from the hydrothermal vents, it's going to kind of happen. And we've done lab experiments where you can make the components of RNA from molecules that we get just from like interstellar dust or like things that we see out there in space. So we see amino acids on comets, interstellar dust, meteors. This stuff just kind of exists out there, the sort of building blocks of the kinds of chemicals that we think formed the first life. And then through these interactions near this energy source and just lots of time and random events, we think that that can eventually turn into something that becomes single-cell life.
And so over this 500 million years or whatever, that occurs. And then we have single-celled life, and then natural selection kicks in a more formal way where the life wants to hang around, and the only the life that wants to hang around ends up hanging around. A different version of the anthropic principle, perhaps.
Well, I mean, you end up with, the natural selection in the form of like the things that are most adapted to the environment
Progress, and the other things don't.
Yeah.
Right. I don't mean to imply that these single-celled organisms were making conscious choices about whether to be here.
Yeah.
Or indeed that any of us are.
Right.
I'm not convinced of that. So then we have this very, very long period.
Yes.
Where life is single-celled.
That's about 1 billion years, I think. Yeah, before the first not single-celled.
Right. So we had only single-celled organisms for longer than we didn't have life on Earth. That's wild.
Yeah, and depending on how long you think this all happened, I mean, the earliest fossils are from like 500 million years after the formation of the Earth, as far as we know. But like, it could have been much, much faster than that. It could have been like some number of millions of years. We don't know exactly, but it could have been reasonably quick that the first life formed out of this chemistry. And then it just took a long time for these single cells to turn into anything that persists enough that we have a solid record of it.
So when you talk about it that way, when you talk about it as chemistry, it doesn't actually seem that different from astrophysics. Like, it doesn't seem totally separate for me that there's a chemistry process that leads to hydrogen becoming helium, or that leads to these massive supernovae creating stable carbon. And then there's a chemistry process that allows amino acids to become RNA. And then there's a chemistry process that allows, is just everything chemistry?
Well, I mean, I would call the earlier bits of that sort of nuclear physics rather than chemistry, but it's all just kind of the rearrangement of matter, yeah.
Right.
Like through physical processes.
Yeah, which makes you think about how everything is just the rearrangement of matter. Like,
yeah,
writing a novel is just the rearrangement of matter, or making a painting is just the rearrangement of matter, right? You're just rearranging paint and canvas into a representation of something.
Yeah, and you're messing around with like information content and entropy in complicated ways.
Yeah. That's so true. You're messing around with entropy when you're writing a novel. Maybe that's the problem I'm having. Need to accept that I'm I'm trying to do something that's fundamentally against what the universe wants to do. I'm trying to make a story that makes sense, and the universe is like, I'm trying to have a little more disorder. That tension is causing me a lot of problems right now, Dr. Mack.
I mean, you'll be comforted to know that at all moments you are actually increasing the entropy of the universe, because you're putting so much blood, sweat, and tears into trying that to make that process of order that it is, the total amount of entropy is still going up.
Sure. Yeah. No. Of course. There's no way that I can. Yeah. And even in that work that I'm doing, I'm increasing entropy.
Yeah. Yeah. Always.
Cool.
Yeah.
That isn't that comforting, just for future reference.
I'm sorry.
This podcast has experienced a lovely reception from the public, but we did get a 1-star review from someone who wondered, is this guy really that anxious? Yeah, anonymous reviewer, I am really that anxious, and in a universe of ever-increasing disorder where everything that comes together will in time fall apart, I have to confess a measure of confusion as to your lack of anxiety. But of course, while there's nothing to be done about entropy, there are ways we can have at least some peace of mind, including life insurance, which can help those you will inevitably leave behind. And with Policy Genius, you can find life insurance policies that start at just $292 per year for $1 million of coverage. Some options offer same-day approval and avoid unnecessary medical exams. Policy Genius lets you compare quotes from America's top insurers in just a few clicks to find your lowest price. And Policy Genius gives you unbiased advice from a licensed expert support team, which is why they have thousands of 5-star reviews on Google and Trustpilot. So don't put off life insurance. Make it easy with Policy Genius. Head to policygenius.com/crash course or click the link in the description to get your free life insurance quotes and see how much you could save. That's policygenius.com/crash course. So a few generations of stars formed supernovae that spread their elements across the interstellar medium, polluting or enriching it, depending on how you look at it. And those elements coalesced to form our solar system. From there, the process was actually quite linear. Nuclear physics led to the formation of RNA, which led to the formation of DNA, which led to the formation of unicellular life, likely near a hydrothermal vent beneath the surface of the ocean. That whole process can seem very orderly, given that all creation creates disorder in the grand scheme of things.
I don't know if this is more or less comforting to you, but it seems like if this process happened on Earth, and it happened probably pretty quickly, then it's very likely to have happened in other places.
Right. It has to have, right? Because, otherwise, the idea that Earth is alone in this just seems kind of absurd.
Yeah. I hear arguments, where it's like, well, we just don't know either way. But we have a pretty good idea of how this chemistry stuff happens in an environment like the early Earth. And we know of something like 5,000 planets around other stars that exist. Those planets exist. And maybe only, a few dozen are what we would call habitable in the sense of being at the right distance from their star. And we don't know anything about their atmospheres. So maybe they're all like Venus. We don't know. Or maybe they're all like Mars. But some of them must have some kind of environment that's not horribly dissimilar to that of the early Earth. And even in our own solar system, there are several places where we think this kind of life might have happened. I mean, we don't have another planet in the habitable zone right now that seems to have liquid water on the surface, but Mars probably had liquid water billions of years ago. A few billion years ago, it seems to have had liquid water. We have really good evidence of that, in fact, that a few billion years ago, Mars did have liquid water. We see evidence of, riverbeds, stuff like that. And there's an active search for, signs of past life on Mars. It may or may not exist. We don't know. But it certainly had conditions that were pretty similar to Earth in a lot of ways in its early history. And unfortunately, something happened where it kind of lost its atmosphere, possibly because the magnetic field failed, because the planet may have cooled down too quickly or something like that, and the atmosphere was blown off by the sun. So it did have a thick atmosphere that was suitable for liquid water. It doesn't anymore. But at some time it did, right? And then the other interesting thing about our solar system is we have several other candidates for where life could currently exist, and they're not anywhere near the habitable zone, because the habitable zone is this narrowly defined, could you have liquid water on the surface of a rocky planet? But what you really need for life is chemistry, an energy source, and water, right? And if you go out to the outer solar system, some of the moons of Jupiter and Saturn have chemistry. We've seen evidence of the right kind of mix of chemicals in those moons. They seem to have liquid water under the surface, one way or another. And they have the energy source of the tidal heating of being in orbit around a gas giant. So they're constantly being like pulled and stretched by the gravity of the planet they're orbiting. So we've got around Jupiter, we've got Europa, Ganymede, and Callisto all seem to have the possibility of subsurface oceans. Europa is a particularly exciting one because we have evidence that there's like salty water under the icy surface. It's like 100 kilometers of ice, and then we think there's like salty water underneath that. And there's some likelihood, we think, of hydrothermal vents under the surface of Europa. I mean, anything could be under the surface of Europa. I mean, there could be fish. We have no idea. But it seems like it has the right conditions, right? And then Saturn, we got Enceladus, which also has very clear evidence of undersurface water. Well, there's like a spray coming out of Enceladus. We can see like venting liquid, coming out of Enceladus. So we think that there's hydrothermal vents probably under Enceladus's surface as well, in this giant ocean that's spraying material out into the universe, right? And then Titan is an interesting one too, because Titan also seems to have probably a subsurface liquid water ocean. We're not certain about that, but it looks like it probably has that. But also it has like a whole like hydrosphere. Like it's got liquid on the surface. It's just not liquid water, it's liquid methane. So Titan has this really thick atmosphere of like methane clouds, and there's liquid methane oceans and rivers and ponds and like lakes on the surface. And then the rocks and things are solid water ice. So you have all these like boulders of solid water ice and mountains of solid water ice. And then you have these lakes, and it really is liquid methane. And I mean, we don't know if anything can live in liquid methane, but it's liquid. It's got complex organic chemicals, probably. Maybe there's something living in those oceans. We don't know.
So it's not just that life, we presume, would be common because it wasn't that hard to make it here. It was hard to make complex life, but it wasn't that hard. Obviously, we've done a bunch of it, right? Like we've got a lot of different life on Earth. It does seem like, correct me if I'm wrong, that we only made eukaryotic cells once. So that seems to have been a big jump. That seems to have been kind of challenging. But we did it. Of course, you don't have to have a eukaryotic cell to have life, and there may be other ways of developing life and everything. And what this makes me think, and I'm interested to see if I'm on the wrong track here, because I probably am, is that it may be, in fact, that life is sort of inevitable if you have these elements of water or some kind of liquid that works, and you have the potential for chemistry, and you have this ability to do energy transfer. Like, it could be that it just happens almost every time.
It could be. Yeah, we really don't know. I mean, it seems logical that when all the ingredients are together, probably it'll happen. But yeah, we really don't know. And there's been lots of efforts over the years to try to quantify our uncertainty in that. And the one that's most famous is what's called the Drake equation. So Frank Drake, who passed away only just very recently, I think within the last year, was this famous astronomer who just wrote down an equation to like quantify how many technological civilizations are there out there in the galaxy we can talk to? Okay, so this is a very specific question. This isn't how much life is there. This is, can we talk to them on the radio, right? How many people can we talk to on the radio? This equation, I should say, is not meant to be like you write down the solution to this equation and it gives you a number and you trust that number. This equation is really about like how to talk about what we don't understand.
Understanding the variables, even if we don't understand the numbers.
Yeah. So the equation is really about like, let's write down what we need to know to answer this question. Let's write down what are the big uncertainties, right? And so there are lots of different ways to write down this equation. One way you can do it is you can say, okay, the number of technological civilizations we can talk to, okay, that's going to be equal to, first you need to know the number of stars, right? Then you need to know what fraction of those stars have planets, which we think, I mean, we know there's a large number of stars. There's like 400 billion in our galaxy, right? Okay. We think that probably quite a lot of them. Most stars probably have planets. That number is somewhere close to 1, okay?
Wow.
In terms of stars that have planets. Then you want to know the number of habitable zone planets per star, right? And that number is pretty uncertain, but it's also probably not that far from 1.
Really?
Maybe like a 10th, somewhere in that range. Like on average.
That's such an astrophysicist thing to say. It's not that far from 1. It's probably like 0.1.
Yeah, or maybe like 0.01 if you're really pessimistic, right? But like,
which is pretty close to 1. It's pretty close to 1 to you guys.
It's within a couple orders of magnitude, right?
Yeah,
like that's
yeah.
as a cosmologist, that's basically 1. Whatever, right?
Round up, round down, you get it's somewhere around 1, between 1% and 90%.
Yeah, these are all very, very uncertain numbers, okay?
Sure, of course. Okay, but you need that.
Yeah, so somewhere around there. And then it gets to the point where we just have no idea, right? Okay, so then the fraction that have life. Okay, that's the next number in this equation. So the textbook that I taught my intro to astronomy class from a couple of years ago says that for that number, the pessimistic estimate is 0.01. The optimistic estimate is 1. We don't actually have any idea, right? Like, we have no idea.
Right, of course, because we've never seen a second example of it.
Yeah, and we have no idea how inevitable any of those steps were that we looked at. Okay, so then let's say that's the fraction of that have life. Maybe it's close to 1. We don't know. And then the next one is the fraction of those planets with life in which some species evolves to intelligence. Okay, so there's the fraction that has life and then the fraction that have intelligence out of the ones that have life. Okay, and again, no idea. The textbook also puts it between 0.01 and 1, but like, we don't know. And that's a funny thing too, because like, I mean, depending on how you define intelligence, that kind of seems to have happened once on Earth, right? Like, and I think about this a lot because, you know, you look at a place like New Zealand, right? New Zealand kind of broke off from other places pretty early on when there were a whole bunch of birds, right? Like everything was kind of dinosaurs and birds. And New Zealand's like native ecology, the native species were just birds, right? Like they have like birds filled all the niches.
And tuatara.
Yeah, and the couple of reptiles, right? So birds filled all the niches, but they never turned into like talking birds. Like, I mean, talking in the sense of like, I mean, they can say, some of them can say some words, right? But
they never figured out like what's keeping the stars apart.
Yeah.
Or got anywhere close to that.
Yeah, they didn't turn into what we would normally call a sort of technologically intelligent species.
Right.
Right. And there was time. There was lots of time. But it was the mammals that went that direction. The birds didn't.
Yeah. Right. And so it really only has happened once. And then when you consider the fact that our species, which is overwhelmingly the most technologically sophisticated species in the history of life on Earth, is about 250,000 years old, maybe 300,000 years old. Brand new, you know, younger than elephants, younger than bears, younger than giraffes, like just brand new. And we don't, you know, we don't know, we know how old we are, but, you know, to get to the unknown unknowns, we have no idea how long we'll be here. We have no idea, like, what the end of the temporal range is.
Yeah, and that's another thing that comes into this equation. It's written in different ways. In this case, it's like the fraction of existence during which intelligent life survives, right?
Yeah.
Okay, so you can write it in terms of like the number of years that intelligent life sticks around before destroying itself or being destroyed by something. That number can vary a lot.
No joke, it can.
Yeah. So that's right. So then it's like maybe it takes a really long time for intelligence of the sort of like technological intelligence to develop, and maybe we don't have that much time where we can exist without something terrible happening, either by our own hand or something else. We don't seem to have any stars nearby that could go supernova anytime soon in an astronomical sense. But like it could have been the case that we could have evolved on a planet that was, you know, next to a big massive star that was going to go supernova and totally sterilize the surface of the world, right? like that could happen quite a lot. We don't know. So that's one of those things that is also a big unknown in this equation, is like, how long do we persist? And I should say, like, I feel bad talking about intelligent life and not including like the dolphins and the octopi, but like octopuses, I guess, is the correct plural. Anyway, but we're talking specifically about like people we can talk to.
Yeah, and we might get better at talking to dolphins or talking to whales or talking to octopuses over time. But in terms of the current technology, there is a different level. Now, it's possible that octopuses tried it all out for us, 50 million years ago, and they were like, this is not good. No, y'all don't want to do this. And they like just went back to living happily in the ocean and doing their thing. We don't know. But like, yeah, I think we have to acknowledge that humans are a little different from other animals currently.
Yeah.
And we don't know how often stuff like this happens. And we also to your point, we don't know how long it lasts, because it's very weird. And it does feel a little fragile because it's never happened before, so far as we can tell. And because we're becoming much more powerful very quickly, like we've only been in the atomic age for one human lifetime. So are we going to be in the atomic age for 5 human lifetimes or 5,000 human lifetimes? I have no idea.
Yeah. And I think it's probably not that easy to do something that would wipe out all human life on Earth. Like, I could easily imagine humans doing something to ourselves that basically wipes out technological civilization, our ability to talk to their planets.
Right. We could slow ourselves down a lot. We could definitely slow ourselves down. And it's kind of hard for me to imagine us. I don't know. Maybe we do. Maybe I need to be a little more optimistic. I was about to say it's hard to imagine us not screwing that up, but maybe that's just the darkness talking. The truth is that we've shown an astonishing capacity so far for adapting to new worlds. Like, that's always been our gift, right? Is the two gifts I think we have are that we can adapt to new spaces and that we collaborate better than almost any other species. I guess ants. But like we have a mix of an ability to collaborate and an ability to reason that's pretty cool.
Yeah, and depending on who you ask, human biological evolution may or may not be significant anymore, but we've found ways to get around that by using our big brains to change our environments to suit us better instead of changing us to suit our environments better. And we have a lot of tools in that direction.
Well, and it's just astonishing to me that we've left our atmosphere. That took so much work. That's so hard. I think if you pitched that idea to humans 500 years ago, they would have been like, that sounds very, very difficult.
Yeah, it is amazing what we've done. Like, the thing that I find so amazing is just how much we know, right? That we've been able to understand the evolution of the universe from basically the beginning to now.
And not just that we know it, but that we're able to share it and pass it on, that we have these technologies that allow us to communicate that knowledge. I think about that a lot in terms of, why the scientific revolution happened when and where it did was partly because of like medical journals and scientific journals and the ability to share information really widely across time and space. And then the miracle of being able to learn from the dead, being able to hear from them directly. Drake isn't with us, but the equation is. I love that.
Yeah, yeah. And there's something lovely as well about the fact that, I guess there's like evolutionary pressure that we like to solve puzzles, right? There's evolutionary pressure for that, making us happy to better understand things. But I think it's also lovely that we like to talk about them too.
Right.
That we like to teach, that we like to share information, that we like to, that it can be enough of a reward just to have the joy of sharing something cool and not necessarily be personally benefiting from that. Like, you see that in the scientific community all the time.
Yeah. The light in somebody's eye when you help them understand something is, maybe there's an evolutionary pressure to do that, but I don't think that's ultimately why we do it. And even where there is no, there's no profit incentive, the narrow incentives don't make sense with something like Wikipedia or with teaching college, where a lot of times the profit incentives don't make a ton of sense, but there's still joy in it. There's still meaning in it. And it doesn't have to be grounded in those incentives. It can be grounded in something else, like something like love.
Yeah.
Love for other people, love for the subject, love for the joy of learning and the joy of sharing it. Like that there can be something there.
Yeah, and it's on all sides. You know, it's a joy to learn. It's a joy to teach. It's a joy to just share enthusiasm and excitement and be part of all of us gaining a better understanding of the universe that we live in and you know, sort of expanding our perspectives and our horizons. That is a wonderful thing.
You've made me feel better.
Good. I'm very glad.
I'm glad we got there. I'm glad we settled on that. It's so true. We're not so bad after all.
We're all right. We're all right. We might make it.
So in a strange sense, our existence wasn't inevitable until it was. Given everything we learned in today's episode, it's not hard to see how life got started, and yet the fact that we exist is still pretty astonishing to me. After all, other planets and moons may be habitable, but there is no other us, at least as far as we know. In one sense, the only thing that could have happened, happened. But I also feel an unavoidable sense of gratitude that matter rearranged the way it did, in a way that formed beings who, in Dr. Mack's words, can experience the joy of sharing something cool. In the next episode, our journey will finally lead us to now. Katie will give us a snapshot of the universe from our present-day vantage point, and I'll ask some questions I've been patiently holding back for 8 long episodes. This show is hosted by me, John Green, and Dr. Katie Mack. This episode was produced by Hannah West, edited by Linus Obenhaus, with music and mixed by Joseph Tuna Medish. Special thanks to the Perimeter Institute for Theoretical Physics. Our associate script editor is Annie Fillenworth. Our editorial directors are Dr. Darcy Shapiro and Megan Modafferi, and our executive producers are Heather DiDiego and Seth Radley. This show is a production of Complexly. If you want to help keep Crash Course free for everyone forever, you can join our community on Patreon at patreon.com/crashcourse.